Okay, in this Unity tutorial, we're going to go and find a way to visualize music over time. So this is kind of like a picture of what we're going to try to do here in this Unity project that I made. We're going to see how I did a thing like that. And for example, this is going to be the end result of the tutorial. I have a song here, music, and I'm going to press play any day now. And what it's doing is it's visualizing the sample, and then that sample just scrolls to the back, and then every new sample is being visualized in the front and scrolls to the back, which kind of gives us, if you look at it from the side, a visualization of the music over time in 3D. Okay, so how did I do that? It's not hard, believe it or not. It's pretty easy. So I'm just going to open up the script here. This is the visualize over time script, and this one over here, this is a game object. Let me just put the visualize over time and turn that off for a minute, and we'll take it a step at a time. First, we'll do the visualize, where it just visualizes the audio at an instant here. See, so here we're just looking at the audio the way it looks at an instant, and we don't have a history of anything. So if we could do this first, then we could do it over time as well. So let's just first take a quick look at this visualizing at an instant. This script is smaller, it's easier. I started off, this visualize thing is actually, I made an empty game object. All right, let me just save my changes. I created an empty game object first, and that's how I got the viz. And then to that empty game object, I just drag and dropped one of the songs here, so I could have an audio source component, and then I drag and dropped the viz script so I could have a script component. So this is the script component, and what it takes is a number of samples to sample from the audio. And the audio function that we're using is called GetSpectrumData from Unity. And let me just show you the properties for that. Unity GetSpectrumData. And there's some rules to that function, like it takes 3 parameters to get spectrum data. The first parameter is how many samples, and it has to be a power of 2, with 64 being the least amount of samples that you can collect. So the max here, it says, is 8192, and the min is 64. So here you could specify how many samples you want to collect right there. And then the channel, because I guess if you have stereo, you got 2 channels left and right, so you can specify what channel you want to sample from. And then the window. The FFT window, that's the fast Fourier transform algorithm that you want to use. And there's a number of algorithms. Each one has its own ability to, so rectangular here is like the easiest one. And let me see if I can go to the FFT here. If we look at the window things, these are the different algorithms for FFT, fast Fourier transform. Rectangular is the fastest one. Triangle, Hamming, Hanning, Blackman, and Blackman-Harris. Each one, basically what it'll do is it will more purely get the sample at a frequency than another one. So with rectangular, you may have like some sampling bleeding into the other sample. It won't be perfect, but of course it'll be fast, you know? All right, so let's take a look at the script for Viz, where it just does that one line. So here I have a script. I don't need this line, bye-bye. And here I just make sure that the audio component is there. And these are the public variables that we're able to specify in the window. And inside the script, I have an array of game objects. That's basically all the quads in the sample. Each one of these squares, why it takes so long to play, each one of these rectangles is a quad. So a quad is the fastest thing I could render, so that's why I picked a quad, so I could keep the frame rate up. All right, so we have to have an array to hold all those since we're going to make them when the script runs and they're not there in design time. And then a pointer to the audio source. So in the start function, reference the audio, allocate the two arrays, one for the samples of the size of samples the user said. In ours, we said 64. And then the number of quads, of course, we have to have one quad game object for each sample to show the height of. And then we got to create the quad objects. So we're going to go here to create quads where, as you notice, every time I press play, it was a different color. And I did that with this here. I made a material within the script. And then I gave that material a random color. Then I go through for all the samples, I kind of create a quad object, okay? And I position each quad object. This is the main, these two lines are really important. The create the quad primitive creates a quad in the scene, and then the positioning so that they're positioned along the x-axis like that, just like that noise. And then I just make all those quads a child of whatever the script is attached to so that my hierarchy window doesn't blow up with a bunch of stuff. All right, and then over here, I just assign the material, which is a random color material, to the quad. And then I add the quad to the quads array. All right, now after that, everything's initialized. Now we just have the update function for which the music is playing. I set the music over here, the audio source, to play on awake and loop. So as soon as the game plays, we come to the update function, and we're first going to use the GetSpectrumData function I just told you about, where we feed it the samples and which FFT algorithm to use. So here I'm allowing the user to specify which FFT algorithm so they can see the differences. Then here we go through all the quads that we have, which is num samples of quads. And we take the sample, which is a very small value, usually like between 0 and 1, and I just multiply that value up so that we could, more drastically see the height change by the meter scale, okay, which was a parameter from the inspector window. And then I scale the quad to be that size. All right, so I scale it on the Y, and this was from when I had cubes, because right now you can't, quads are flat, so that could just be a 1. All right, and then that's basically it. This is the whole script. There's not a lot to it. The main power of the script is coming from this function, GetSpectrumData, which is part of the audio source in Unity, and that's how we do one line of visualizing the audio. And let me just see the different FFT algorithms. If I try Blackman-Harris, see it's a little bit more restrictive on the volumes there. And if I try rectangular, you see how it just kind of sums up more stuff. It's not as restrictive. It's not as accurate. And this is recording by the volume here. So if I did make the volume lower, the lines are shorter. And if I did make the volume higher, the signal strength is bigger. Okay? And also, this is actually showing in speed. So if I slow down the pitch, oops, I slowed it down a lot. All right, so that's one, and that should be easy to understand. Now here it is when it's going over time. So basically what I did was I tried to take the one signal that I had up in the front, and I put that on a, as you can see here, I have a bunch of lines. Okay, so right now there's 64 line game objects, and each line game object has all the quads that I'm sampling. Okay, and that's just so it's nice and tidy in the window. So what happens is the first one it shows the samples on on whatever line's in the front, and then everything scrolls back. When something gets to the end over here, when one of the line objects gets to the end, I just reposition it back in the front. Whatever's in the front is what I show the spectrum data on. So what does that look like in a script? Well, here I have the number of samples again, which we understand that's how many samples I'm using in the GetSpectrumData. And then the history is how many lines back do I see at a time. So here it's set to 64. I could set it to just 3, 4, 2, whatever. And that's how long the history will see. And then the meter scale is how much I multiply the value by. So you could see the height. So now the viz over time script, it's similar to the viz script, a little bit more complex. I make sure I have an audio source. These are the public variables. These are the ones that the user could assign here. And then samples is just there to show what the sample values are as the music's playing, which, I'll let you see that. Let me see. I'll press play. So there's 64 samples I'm requesting, and these are the actual values that are being multiplied and displayed. And you see how they're all very small values, like 0.000 something, and that's why I needed the meter scale. All right, and then I have to have something to hold all the game objects. So the game objects that I am going to be working with are the line objects. They're the parent. Each one of these things is going to be a line, and then to each line I'm going to add all the little quads. They're going to be children of a line. So in my script, I just have to have a reference to the line game objects, okay? And a reference to the audio source. Also, you notice that even though the smallest sample I could do with the GetSpectrumData is 64, I'm only going to show whatever count sample show says to show. And that's because most of the data, when you're looking at the visualization, it's down here in the lower frequencies, and up in the higher frequencies for this song there's not much. So I kind of just focused on the first half of the data, and that's what this variable is, count sample show. See, and right here I set count sample show to equal half of the num samples, so only equal 32. All right, so just like in the other script, the first thing I gotta do is I gotta create my game objects that I'm gonna show this stuff on. So I'm gonna create an empty game object, right? And then I'm gonna position that empty game object in space at 0, 0, 0x, and 0y. But each one is gonna move forward along the z-axis, which you could see, where's my z-axis? See that blue? It's going to move forward. Each one I place the line empty game object is going to go forward along the game axis, the z-axis. And then I'll set its parent to be the thing I attach the script to. And I just give it a name so you guys can see which one we're talking about. So there's the parent object, the line. And then I create the child objects of that line, all the quads. Okay, so primitive type is quad. I set the parent and I set the position. S is along the x-axis, like which quad it be, and H, I noticed I was setting this to 0, thinking, but I had to set it to H. I may have to clarify what's going on, but anyway, I set the H because I wanted it to be back on the line that it belongs to. I thought that since this was a child of the line, it would be back. Anyway, S and H, blah, and the quad name. Okay, so now I got the line with its children. Now I put that in my lines array. Good, I'm all set up. I got my objects in the scene. I'm ready to go. Here comes the update function. This is the function with all the power. I get the spectrum data, and then I visualize it. So to visualize, it's going to take, I'm going to keep track of what the closest line is. That's the line that's up in the front, because that's the one I want to apply my spectrum data to change the way the line looks. First thing I'm going to do is I'm going to shift all the lines forward on the z-axis. So something's here at 0, 1, 2, 3. They all shift. And then whoever the last one was is going to come up to the front. So that front line is the closest line to me, the closest line to the camera. And I'm just going to take that front line and visualize each sample along each quad of that line by scaling it on the y-axis. And really, it's just that simple. There you go. I press play and we could see it happen. And I could do this with different songs like I did in the other visualize audio. I have some other musical samples here. Let's see, that was number 6. Let's see number 7. Boom, boom. Then I can see number 5 over here. And number 4, which is something I found with the highest pitch that I could find. A bird singing. And what's this fat one over here? So one thing I noticed after visualizing the song over time is that if I look at it from the side, maybe I could determine the tempo or how many beats per minute the song is by these like spikes. If I could just measure the distance between the spikes. So that's what I'm going to do in the next video. I'm going to see if I could come up with a meaningful way to detect the tempo, how fast the song is playing by beats per minute. Just somehow trying to take this information I see on the side here. But that's it for this video. This video was about visualizing in 3D the sound over time. And enjoy. Bye. There you go.